Hello, I'm Glenn Steeper, the Director of Growth and Solutions here at Glencore Technology. Welcome to today's webinar. The title is Comminution 2025, Stirred Milling Testwork and Energy Benchmarking. Today we have Jon Gurnett and Kai Johnston, metallurgists here at Glencore Technology, who will be presenting the content that they presented at the Comminution 2025 conference in South Africa. Just some quick housekeeping. You'll find you are muted. Now, this is to keep things quiet for the webinar. Please ignore the raised hand icon. Use the Q&A icon for any questions. And on that, feel free to ask any questions anytime along the way. At the end, the webinar won't be closed straight away. We'll actually be sitting there quietly in the background taking your questions. So please keep asking questions all the way to the end. So on that, over to you, Jon.
Thank you. The title of this presentation is a recap from Comminution 2025, and this was Improved Performance in a Stirred Mill, the Hidden Trade-off. Now, when I originally came up with the concept of this, I was thinking about looking at other sites and how the material selection can actually influence the overall specific energy and how it's very rarely looked at on most sites. But after seeing the results of a pretty poorly run component trial, I thought I could expand the scope of this presentation and provide a bit of guidance how to do trials in any stirred mill, but I will use the IsaMill as a case study. Now, the agenda will be quite simple. Small material trials and the SGE effect, so specific grinding energy effect, how to do component trials, guidelines, or what I like to say, best practices for doing component trials, and a bit of a conclusion. Now, those that may not be aware, I've got an internal image of the IsaMill to my right. That is a cutout. Those that don't know what an IsaMill is, it's basically a stirred mill, a horizontal stirred mill. We pump slurry in between 50 to 150 kPa, and it enters a chamber with a series of discs on a fixed speed shaft. Those discs rotate anywhere between 18 to 22 meters per second, and what that does is it creates this highly agitated environment where we mix ceramic media and the slurry. The tip speed causes the more coarser stuff to move out, and the fines move through the center. Once we get to the end, once we get to that yellow part called the rotor, we find that the gap between the last disc and the rotor actually pushes fluid out towards the edges, and the rotor acts like a pump towards the edge of the mill. This is important because what happens is anything coarse that moves out has to be ground before it can leave. This is why the IsaMill has that high internal classification that we always seem to talk about. So now that you know what an IsaMill is, let's go on and work out how we do some trials. But let's start with material trials, the effect on specific energy. Logically, if you grab steel or rubber, there is a difference, right? Steel is hard, rubber is soft. If it's hard, it won't absorb energy, and it will be more a shearing motion if you use that component to stir. Rubber is softer. It will absorb energy. It will shear and almost catch and accelerate media. If the mechanism is different, just thinking about the hardness and the shape, surely the performance will be different. That's true. So on the graph on the right here, we have an optimum stress energy curve. Please go through my paper, and there's some literature on this, on how you can actually scale this up. And what I really want to point out is there are two distinct curves, one above, one below. The one above is a polyurethane chamber with a polyurethane disc, and the graph below is a ceramic chamber and a ceramic disc. The lower the graph, the more efficient it is, hence the optimum stress energy curve. So what does this actually tell you? In a convoluted way, it's telling you materials matter. Type of material you use will change the optimum stress energy and hence provide a different performance. So material selection is important. Now, in most applications, we know that once the mill's installed, you want to get the best out of the parts, right? So you will trial things, but you don't normally go back to the laboratory. So what we did here is do an example with 3 discs. On the left, we have polyurethane. In the middle, we have a Duro 40 rubber. And on the right, we have a Duro 60 rubber, the black one. Now, they all look the same. So performance is going to be the same. this is what we're about to show. If I do a signature plot, so the signature plot is a small scale laboratory test we use to size the IsaMill. We do a batch pendulum style mill, and we pump at steady state enough sample through the mill to measure a set size reduction, to measure the energy to go from one size to the other, and we go backwards and forwards in a pendulum style manner to build that curve. That curve you can see has size on the bottom, specific energy on the vertical axis. You can see there is a linear relationship. If I look at this with all three graphs from a distance, it looks pretty similar, doesn't it? It's not really much difference in performance. But let's look in a little bit more detail. For me, if I look at 4 key points, 30 micron, 25, 20, and 17 micron, and actually look at the difference between those curves, I see there's a linear offset anywhere between 10 to 17%. To me, anything greater than 10% is quite significant within a mill and outside its normal standard margin of error. So if I was looking at this, the Duro 40 is actually less efficient relative to the Duro 60 and the polyurethane. What does that mean? Well, in practice, it means that the Duro 60 is harder than Duro 40. It has similar behavior to the polyurethane. And if I was taking this part into a full-scale mill and I wasn't aware of this, it would indicate that a Duro 40 component would require a higher media loading and a higher power draw to achieve the same P80. And this is normally the best practice to do it in a lab and provide guidance on these tests. So just because a part looks similar and a vendor tells you it's similar, it is still worth testing because there may be a hidden consequence. In the style of, for the IsaMill, we move into a Duro 40 component. It's not actually a big deal because we normally operate at a media loading of roughly 70%. So there is room to add more media if required. It's just being aware of that. Other technologies do not have the same luxury of changing that. Now, where did those parts come from? Where did those rubbers come from? Well, it's a long process to come up with what we're going to change our components to. And Glencore Technology has been testing components for nearly 25 years. Nearly 30 now, actually. We test these in an M10,000. M10,000 naming convention for our mills is M for mill, and the number is the capacity and volume. And what we do is we put these in an abrasive grinding duty, such as a magnetite, a platinum regrind duty, or a medium inert, mainstream inert grinding duty. And these are put on the non-drive end flange, NDE flange. The non-drive end flange in the mill is where the feed is. And the reason why this is the most abrasive grinding environment is the rotor in the design pumps the media towards the feed end of the mill. So most of the media and most of the primary grinding happens in that zone. And that gives us the best context to what it's going to do to wear components. So how do we do this? Well, we put the pizza flange in. So we have a creative name. It looks a bit like a pizza. And we put control pieces next to compounds we know. We then measure the wear relative to each other to determine what is the wear rate and whether it is something worth pursuing for other components. And on the image on the far right, you can see that after a couple maintenance cycles, how they sit relative to our red control samples. Now, materials that we have trialed have ranged quite significantly. We've trialed polyurethanes, tungsten carbide, ceramics, Duro 40, 50, 60, 70 rubbers. We've tried many things. We run these trials anywhere between 6,000 to 10,000 hours. That's important. And then we measure it relative to the control. So if you look on the graph on the right, you'll see control samples are the lower wear rates. And then I've not named the wears, not named the materials, but the numbers are different types of materials. And as you can see, they don't actually stack up to the control wear rates. And also an interesting note is a Duro 60 rubber and a Duro 40 rubber can be very different depending on the rubber supplier because they are actually designed for different duties. So you can actually test multiple types of the same rubber without even realizing. Once a material has demonstrated good wear life through these tests, that is when we would consider doing and changing mill components with it. I hope that makes it clear. Now, component trials. Component trials are inherently more complicated than material trials. Material trials fundamentally will have an effect on wear rate and life of component. Component trials affect the flow within the mill, the internal behavior of the media, the movement, and if not done correctly, can actually be quite disastrous. One of the best things to do before you change your component and potentially save yourself a very expensive maintenance exercise is talk to the OEM to see whether it is something worth pursuing. When we test material selection, we prefer on-site pilot mills, so either an M20 or an M100. The M100 is preferred, and we want to compare them against existing installations for benchmarking. This is very, very important. On the M4, changing components on the M4 can demonstrate impressive results, but these do not correlate to a full-scale mill. We operate at different speeds, different flow dynamics, and what you'll find is what may be successful on M4 will destroy your mill. So when we do these component trials, we model the discharge geometries and shell liners that we prefer, and we actually print polyurethane discs as they're quicker and cheaper to test than do an expensive, arduous modeling exercise, as these provide guidance on best behaviors before taking up to a M10,000 style trial. I've got an example here of a few discs. Since feed is variable on most plants, you can't exactly look at the same F80s for each test and determine your specific energy. So what you can do is you can actually look at the upgrade. So what your feed is, your P80, and then you can actually measure the difference, and that gives you your relative upgrade for different speeds and media loadings. Now, that's important to see, because if you look at this graph right here, you can see a high reduction ratio for a high grinding power, and that point on the far right, a castellated design, looks like it's significantly more efficient. The way you should interpret this is it's not about where it sits on the graph, it's the relationship and the slope of that line. To me, those slopes are all very similar. It's just the amount of power that the disc can actually draw. It's not actually the improvement on grinding efficiency. So to me, all the graphs, all those discs we tested show the same sort of relationship on an M20 level. And so none of them have shown failure to the point where we wouldn't take it forward to M100, M500 style trial. Now, I talked about that point that was far out there, the castellated style disc. Since it's a linear behavior, the upgrade ratio suggested no difference in energy efficiency. Just because a disc draws more power does not mean it can effectively improve the process. So we took that disc from what we've read in literature, and we took it to another scale up to see what the wear implications would be on a full-scale mill. So here's an example of discs on the right. Now, these castellated discs will provide, when we put them in an M100 style mill, they behaved almost like what I expected. They provide improper mixing. The mixing gets thrown throughout the chamber. The media does not sit towards the feed end, it is thrown everywhere. This is not what's seen on a pilot level, on the M4 level. This causes damage to your drive end flange. Your media will sit towards that end, and as you can see here, you can see all that media sitting within the discharge screen of the rotor. The media is sitting there, it's interacting, which means it's chewing that area out. Since it's all sitting there, the media is no longer behaving like a fluid. The media is crunching as well, and it's actually destroying the media, hence further reducing the efficiency. This all goes to the point, if it draws more power, it doesn't necessarily mean it actually is more efficient. After this trial, we stopped progressing this design because we recognized how much damage it's doing to the mill, and we wouldn't want to push that sort of design onto our customers. The reason why I'm highlighting this is just to show you we do evaluate these disc designs, and we progress what we think is the best design for the end client. Now, guidelines for component trial success. This is important. If you're going to run a trial, you need to, first of all, set some guidelines. Define what success looks like. What does a component have to do? You'd be surprised how very few people know this. Does it have to equal what you're doing? Is it to have to be cheaper, or does it have to be more efficient? You have to be clear what you want that component to do. And secondly, optimize the mill to ensure that the mill is running as efficiently as possible before you do the trial. Otherwise, comparisons do not allow for a fair comparison. You will grossly exaggerate what the disc can do or the shell can do. You need to make sure everything's in the best condition before you run. You want to ensure the base case setup is comparable. I put a polyurethane disc in. I need to compare it to a polyurethane base disc. As you saw at the start of the presentation, different materials affect different properties. You want to ensure the same volume type of media charge is being used. You want to remove the variables that can influence performance. By doing this, you can show what a good trial is. If I don't optimize a mill circuit before I run it, it doesn't allow a fair comparison. How many people have done reagent trials and shown great success? Was it the reagent, or was it because people are actually looking at the circuit? It's the same point. Now, if I'm going to survey a mill, there are some key things I need to survey. I'm not going to go into too much detail here, but what you want to look at is your IsaMill discharge and your fresh circuit feed. So your cyclone underflow in this open circuit arrangement. You look at fresh feed because the IsaMill feed has a recycled stream from the discharge, and that can bias the result. So you always want to look at the fresh feed, and that's what we do our SIG plots on. The discharge, obviously, because you're measuring your size production for your energy input. You also want to go through about a month's worth of process data as well to see how the mill's performing, make sure there's no upsets, and check the stability of the circuit. I've also got the survey sample points, so those purple crosses on the cyclone. One of the key things for this is many times when we do site audits, there are complaints or feedback that there is issues with the mill producing slimes. Quite often when you do the analysis, it's a bimodal feed to the next part of the circuit generated from a difference between the cyclone overflow and the mill discharge. If you get those two similar, you'll actually improve your performance a great deal. And so that's what we do. And so in conclusion, I wanted to let you know that material selection will influence specific energy. This is pretty clear cut. Component trials should be at a minimum of pilot level. Don't trust M4 level tests because they can severely grossly exaggerate performance. And if you do at a pilot level or larger, upgrade ratios are a good method for fixed medium volumes to show promise of discs and shell liners. Define your success criteria before the trial. What's it got to do? Is, for example, 3 months life good enough? 6 months, 9 months? Define what you need to do. And lastly, optimize your mill circuit before any trial is run. This ensures that any gains in performance are not grossly exaggerated. Thank you. Any questions, please put them in the chat, please. The title of today's presentation is Specific Energy, the Race to the Bottom. In my day-to-day work, I deal with quite a lot of test work, quite a lot of signature plot tests, and quite often we'll do these tests. We'll go to EPCMs and we'll talk about the test work result and where the energy comes from. And very often we get queried, that doesn't look right. That looks too high. Can you please come and explain? And so from these conversations, I gained the inspiration to try and do more of a cause and effect presentation on how to manipulate your energy in a test. Now, instead of calling it a cause and effect presentation, I don't think there'd be much interest. So I decided this can be really more a benchmarking guide on how you can lowball your specific energy in the test work phase and provide some guidance on what to look for when looking at vendor tests. So with that, let's begin. Now, the agenda. I wanted to give you a very high-level summary of vendor tests. I want to just do this as it's been published before and just gives you a quick reintroduction into what we're about to discuss. And then I'm going to go through some tricks how to make your test work look more efficient compared to competitors. These will cover specific energy, mass of the sample, media, actually how you interpret and characterize the particle, and then just give you a bit of a conclusion on how to make it look more efficient when you do your tests. So let's begin. So what is a signature plot test? Signature plot test is technically an operating work index test that's performed in the laboratory under steady state conditions that reflect a full scale plant. Now, I wanted to cover this specifically because when we look at test works, it never comes to the same scrutiny as you would expect a primary or secondary milling circuit. In these circuits, they incorporate roughly 70% of the capex of a plant. And what we find is that there's a large variety of tests out there in the market, and they are heavily scrutinized. And in those situations, we don't use an operating work index to size the mill. We use it as a test to measure the efficiency against the theoretical capacity. Whereas when you start looking at stirred mills, there seems to be a lot of trust on the vendor, which from my perspective, I quite like. But what I'm here to do is really point out that when we size these mills, we do it on one or two operating work indexes, which we call a signature plot. And they are rarely scrutinized by industry and rarely challenged. And what I'm trying to do here today is provide a bit of education on a few of the key aspects which I think may be of interest to you moving forward. Now, what's quite common is we don't use the bond work index, and that's pretty much well established. Bond's theory, as you know, proposes an exponential energy of minus 0.5, and this is well publicized and is a very good approximation to 100 microns. Once you get to fine grinding, sub 100 microns, this changes significantly. This is well published, and as you can see here, the exponent changes depending on the ore. So, what's that mean? We can't really use the bond work as a good measure. And if this is something of interest, I have other published examples, and please feel free to reach out in the comments and I can send them to you at a later date. So we can't use a bond work. What's out there? We have four key tests we can use. We have a Vertimill test, we have a VRM HIGMILL test, we have an IsaMill test, and SMD. What I've got here is I've broken up the section into 5 key areas. How you infer energy measurement, if there's scale up, the grinding chamber volume, what's the normal sample size in the tests, and the media. Is it selected for a specific duty or is it standardized? And what I've done is highlight a few key aspects in red. And these are key differentiators, which I'm going to go into a little bit more detail later on. With energy measurement, we measure it by a VFD. Everyone else measures torque. What's the consequence of that? I'll go into that in a bit. Scale up. What is claimed to be scale up? What is demonstrated scale up? And actually, I'm even going to ask you, is scale up even important? Grinding chamber volume, that has a big influence as well. Sample size, 15 kilos is a lot, but there are reasons for that, and I'll go into that in a bit more detail. And the media, why it's important. So let's begin. So before we begin in full details, but let's just ask a hypothetical question. In stirred milling, scale up, is close enough, good enough? From a vendor perspective, we always get it must be 1-to-1, and that's fully understandable. But what we actually see in industry is close enough seems to be good enough when you go back and look at installed installations. This is important. And it's not just me saying that. There are examples, and I will go through a couple. If we start at Newmont's Cadium mine, part of the CPF expansion, this was published at MillOps in 2024. We found that for the tower mill that was installed, a Nippon Enric tower mill test, 11 tests, modified 11 tests was done. The average energy was used, and they decided to go with a mill larger than what was actually recommended. Guess what happened? They installed it, and then they found that was about operating work index was about 10% above design. This isn't new. The Emira campaign reviewed tower mills back in about 2010. On the graph on the right, you can see the size reduction on the bottom axis, the operating work index on the left axis. You'll see the vendor estimates all sit below the actual measured in the plant. There are various reasons for this. There's an indication that is close enough, good enough. Well, with screw type mills, apparently it is at this stage. Now, this is not only limited to screw mills, screw type agitators, this is also limited to disc style mills. We have an example of Aero Copper in Kariba. It's originally sized to 7.6 kilowatt hours per ton. Recent papers suggest 16.6. Sunrise Dam, the example on the right. Variability at 10 microns is between 40 and 90 kilowatt hours per ton. There's even a paper by Alton et al., which if you read my paper associated with this, you'll find that only 1 of 5 surveys demonstrated 1-to-1 scale up without a factor. So there's a lot of evidence out there on the lack of accuracy on scale up of these mills. So that's why I'm asking you hypothetically, does scale up matter? Because there are ways a vendor can get around that and re-demonstrate and lower their energy without it really being that obvious. And hence why we're here today. So I want my regrind test to look really efficient, and I want to demonstrate energy efficiency. And how do I look most efficient compared to my competitors? How do I do it? Here we are. So I identify we have different power measurements. We have torque, we have VFD. The IsaMill is the only one that uses a VFD. So that's a bit different. Let's evaluate it. So what we did was we modified an M4. We put a torque meter on a shaft, and we measured the power by the VFD, and we measured the power by the torque meter. We had a supplier calibrated torque meter that was installed, and we had a signature plot conducted by an accredited operator on an M4 under steady state conditions. Steady state implies there is sufficient sample present. The result of this is if I look at torque as my method of power, I'll underestimate between 13 to 15% compared to the VFD. So that's not really an apple for apple comparison, is it? It's a completely different method of power measurement, and there are consequences to the comparison. So if I want to look more efficient and I'm on an M4, I'll just use torque as my measurement. Steady state. Steady state is a good one. I mentioned the 15 kilos. And the reason we have 15 kilos is the theory states every voidage in that mill must be filled 3 to 4 times over. Once that's happened, you will have achieved steady state in a stirred mill. That is very dependent on your solid SG. So the bigger the mill, the more sample you need. With a 4-liter mill at 70% media loading, you need 15 kilos to hit this mark. And to demonstrate this, there is a 5 kilo procedure out there, and we replicated it. So what I did was I went to a site, I sampled the fresh feed, and I generated the signature plot. The signature plot is the graph on my right. Like the other graph, size on the bottom, specific energy on the left, on the vertical axis. The dark blue line there is each pass through the M4 plotted, and it's done on a log-log curve. As you can see, there's a linear relationship. We then surveyed that full-scale mill, so taken the 4-liter results and then looked at the 10,000-liter mill, and that where it was operating sits bang on that curve, 1-to-1 scale up. Now, coincidentally, at 5 kilos left over. So what's worth doing? The 5 kilo test that is out there in industry. So I put that test in, a sample in, I followed the procedure that's available online in the literature, and then I took the samples and then analyzed them. What happened? It's about 30 to 50% under in specific energy. The whole curve shifts to the left. Why is that? If it's not at steady state, coarse particles hold up in that mill, and you bias your method, bias your result finer. So your coarse is retained, and I'm sampling the product. I'm only going to really sample the fines, so my energy appears less. It's not less, it just appears less. So if I want to look more, I just won't run enough sample, and that's one of the things out there. Mass of beads. This is a little bit more complicated, but a little bit more logical. If I go to mill, more beads, more probability of interactions. More probability of interactions, more likely that I'm going to have more grinding. It's only logical. So if I did a test where we put 3.2 liters versus 2.5 liters of media into a signature plot. What we found was it shifted the curve to the left. And so theoretically, with 20% more, well, with an extra 15% more media loading, I was able to reduce energy up to 20% on the fines fraction, sub 15 microns. That's pretty substantial and logically makes sense. But this isn't new, and this is rarely actually looked at when people evaluate test work. It is in the literature, and this is out there. This is an in silica mill for example. And what we've done is I've pulled it and look at my paper to find the source. But what they've done is they've changed the voidage within the mill, i.e. the media loading. And what you can see in that graph on the right is the more the media loading goes up, the more your curve shifts to the left. So at 85% media loading, it looks like the most efficient curve. Therefore, it is the most efficient, isn't it? Well, no, it's not. What you can do is if you look at a specific particle size times the voidage by the specific energy, you actually generate a linear relationship. This is one of the reasons why a full-scale mill and a small-scale mill can actually scale up. So if on the test work phase and I want to demonstrate more efficiency, I can just put more media in the mill. And very rarely in these tests is it normalized between vertical and horizontal style mills. Food for thought when you're reviewing them. So if I want to look more efficient, run a higher meter charge. Sample segregation. Some mills, you can't actually collect the full sample on the discharge. You have to stop the mill and take a sample. It is hard to do this, and it's hard to do well. My colleague will discuss laser sizing in some detail, but you need to ensure tests are run at steady state. And the amount of effort that goes into a stirred mill test, you want to ensure that you actually sample properly. And so, for example, when we sample on the Malvern, we use a baffled beaker, and we're very precise and very consistent in our method. Some technologies, like I said, you have to stop the mill, take a sample. If there's anything coarse in there, you will get segregation. And if you do segregate, you do bias your result fine. And laser sizing. Shape matters. Like I said, my colleague will go through the particle sizes in a bit more detail. But if you look at that image of the two particles, characterize that with a single value. If it's a sphere, it's 39 micron. If it's not, you'll find that you have either 100 micron or 20 micron. This is important when you interpret data. If you use the wrong method, you can look inefficient and have other issues. In the example I've got in the bottom right, this is a tertiary mill regrind. Just changing the particle sizing method and the interpretation reduces and shifts the energy curve to the left by 30%. Understanding particle sizing methodology is key. And if you're picky with it, you can actually bias and appear more fine, as you can see on the signature plot on the right here. So, in summary, the aim of this presentation is not to pick at different tests. The aim is to provide the tools for you to review specific energy and allow proper benchmarking and a bit of understanding to critique results. When we do the signature plot, it can be painful getting 15 kilos of sample, but we know it will scale up 1-to-1. And if that's important to you, these are the reasons why we do the test. And in summary, if you really want to look more efficient, what do? I've got the table on the right. You use less than steady state requirements for your sample mass, you will look more efficient. If you want to measure torque or VFD, torque will always give you a lower result. Run a higher charge of beads. That will then appear and lower your specific energy. Have a little bit unrepresentative sampling, that will also shift your curve. And if you're selective with your particle sizing methodology, that also will shift your curve as well. Thank you. If there's any questions, please leave them in the comments. Thank you.
Thank you. Title of today's presentation is Particle Sizing Measurement and Stirred Milling Test Work in Micron-Scaled Pitfalls with Powerful Consequences. The concept of this paper has come from an industry lack of understanding of sizing techniques and how significant of an impact this has on stirred milling test work. The agenda for today's discussion will be to introduce the background of laser sizing and screening, which are the two most common sizing methods used in IsaMill signature plot test work, demonstrate the effect of both techniques on a signature plot with an IsaMill sizing as a case study, and to provide tips and tricks for determining sizing issues in stirred milling test work. To introduce this topic, the signature plot is the scale-up method procedure for the IsaMill. The test allows for one-to-one scale-up from laboratory to full-scale conditions by replicating the same conditions in both environments. The batch pendulum arrangement, as pictured, uses sample solids volume 3 to 4 times the active grinding voidage inside the mill to achieve steady state during the pass, and so that no feed short circuits the mill, like what you get with recirculating tests. Test work is completed by accredited M4 laboratories worldwide, where testing conditions are nominated by GT to suit both your feed and product conditions for your project. And these results are reviewed as part of GT's quality control process. All technicians must pass an accreditation test every 2 years to validate mechanical performance of the mill and procedural competency of the technician. This ensures that standards are upheld and one-to-one scale-up can be achieved. Interestingly, the most common source of error in failed accreditation attempts and signature plot tests is to do with laser sizing, which has inspired the theme of this paper. So, to kick things off, we'll introduce the laser sizer, so to start this off, imagine you've been asked to measure the size of a cylindrical particle with 20 microns in diameter and 100 micron in length with one singular characterization number. You could opt for measuring the length, but that doesn't tell you much about the diameter, or you could opt for measuring the diameter and that doesn't tell you much about the length. What you find is that characterizing this particle with one singular number is impossible. The only particle that can be characterized by one singular number is the sphere. Now, let's convert this particle to a sphere with an equivalent volume. This would result in a 39 micron particle size, which is very different to the cylindrical particle as we've shown before. This conversion forms the basis for how laser sizers report measurements on particle size. So how does the laser sizer measure the particle? Well, it relies on the angular variation in light scattering as a particle passes through a beam. Coarser particles, as pictured, scatter light at smaller angles with greater intensity, while finer particles scatter light at weaker intensity and larger angles. Both angular variation in light and intensity is measured to determine a volume, and this is converted to a volume equivalent sphere. Now, because of its accuracy at measuring the sub 38 micron particles and its ability to achieve consistency, this has become the gold standard for sizing in stirred milling tests. Now, while laser sizing is typically preferred in stirred milling test work, screen sizing is an alternative method that can be used for stirred milling tests. Measurements in this case are collected by passing a known mass of sample through successively finer aperture-sized screens, and the masses collected on the screens are measured to give you a particle size distribution. Now, the nature of this sizing method is physical, and this means that irregular shaped particles can self-orientate and pass through apertures and essentially report finer than what the laser sizer would produce. And this is what we like to call the shape factor. Now, the amount of fines that are allowed to pass through apertures can change with the screening duration, and this is why that strict standards for procedures must be adhered to achieve consistent results on a screen. The measurement technique also faces challenges with large volumes of near-sized particles, which can blind up apertures. This becomes more prevalent when you measure samples sub 38 micron. The sample mass, where too much can create a bed of solids that prevents fine particles from passing through nominal sized apertures, and clay-containing minerals, which can form agglomerates, essentially biasing results coarser as the fines clump together on a coarser aperture screen. However, now things to note is that the main differentiator between both laser sizing and screening is that the laser sizer assumes spherical particles, whereas the screens is affected by particle shape. This is why the size distribution should be measured across a singular distribution with a singular method where possible. So, now we've introduced both the sizing methods, I like to call this section comparing apples to oranges in a signature plot. These next slides discuss how both sizing techniques can influence signature plot results, and unfortunately, while it does sound obvious, the difference in results is stark and poorly understood. In this example, in this copper signature plot, is the difference that screen sizing has compared to laser sizing. When going from laser sizing to screening, the specific energy is reduced by 23%. As you grind finer, this difference grows by up to 48% with finer grinds. So, as you can see, this has a significant impact on specific energy results. Now, why is this important? Well, if the mineralogy wasn't understood prior to the test, and if different grinding tests were undertaken with different sizing methods, then this improvement in this improvement in particle size reduction could be mistaken for grinding efficiency that does not actually exist. How significant of an effect will this have on my flow sheet? Well, now let's explore a real-world example with a case study for an IsaMill sizing. If you were to design a circuit with a throughput of 70 tonne an hour and a 30 micron grind size, the laser sizer from this test would achieve 47 kilowatt hour per tonne specific energy, while the screens would achieve 27 kilowatt hours per tonne. Taking this to a sizing, an M15000 would be recommended for the laser sizer, whereas an M7500 on the screen size results would be recommended instead. So this shows that being unattentive to sizing method can have powerful consequences on your project. To most viewers, this problem presents itself as a procedural issue for the vendor or lab to rectify. However, if you find yourself performing technology trade-offs between regrinding test work, you need to consider whether you're comparing apples to oranges. Benchmarking using stirred milling test work should be compared to the same consistent characterization method. For example, if you were to measure the particle size distribution of one test on screens, you want to keep screens consistent for all the other tests. Furthermore, if screens are used to determine the optimum grind size test work through flotation characterization test work, then running a signature plot on a laser sizer may overestimate the specific energy requirements to achieve the same P80. So, now that we've established that size matters, here are some of the particle size measurement red flags to look out for when interpreting stirred milling test work. Mineralogy is the first red flag to look for, and this table has been prepared as a guide to assist with determining whether particle sizing or shape factors are going to be introduced in your test work. If you find that your sample has a large presence of any of these materials, we consider this a red flag and the sizing approach may need to be reviewed. For example, magnetite, we always recommend screening only, as these particles agglomerate through the magnetization of the mineral itself. Whereas minerals like talc, mica, and muscovite have thin and platy crystal structures and can introduce shape factor bias on testing. For these results, it may be worth doing concurrent screens to laser sizing. Now, most stirred milling tests only report on P80. Now, while this is a standard number for characterizing particle size distribution, it doesn't give us much insight into how coarse or fines are performing in a size distribution. The unaltered normal size distribution can provide key insights into what's actually happening inside the mill. For this reason, understanding the P98 performance is also a useful metric. Steeper P98 curves relative to the P80 or increasing P98 to P80 ratios, like what is pictured, are abnormal in IsaMill test work and therefore is a red flag. Results like this could indicate coarse retention inside the mill, which should prompt a thorough review of test work conditions. In this particular example, however, viscosity was in range and was consistent. The power draw measurements were consistent, media was on spec, and the feed size distribution was tight with a non-bimodal distribution. Having explored all potential causes, coarse particle retention was ruled out in this test, and that led us to believe that this test was influenced by shape factors. This was confirmed with screening, where a 10 micron reduction in F80 was reported. Now, crystal morphology is another method that can help determine if shape factor bias will influence your test. This provides a visual snapshot of particle shape if this technology is available, and can highlight the presence of particles with high aspect ratios. And this result here showed that there was quite a lot of those shape factor or thin and platy materials. The signature plot that this sample was retrieved from saw significant shape factor bias, with the laser sizing results achieving 37 microns, whereas going to screening achieved 25 microns. Continuing on with particle size distribution, R-squared regressions below 0.9 in either of the P80 or P98 curves are a red flag. This value not only shows how the data fit, how closely aligned a best fit is to the actual signature plot data, but it can help determine if sizing errors or issues are present. In this test, the P98 ratio increased up to about 9, and the R-squared value was 0.64. Shape factors were identified which show the shape factors that were occurring in this test effectively gave this trend. And after screening, the pass 1 P80 dropped from 32 micron down to below 19 micron. The impact, the reported specific energy, was overestimated by more than 65%. Now, it is easy to blame this trend on poor milling performance. In fact, an engineering company has even published this as an example of the IsaMill not being able to grind properly and experiencing coarse particle buildup. However, in actual fact, it was just a sizing issue and shape factor bias had influenced results. This result serves as a good example of being aware of particle sizing methods, and I hope that this raises awareness to question results that achieve R-squared values below 0.9. Agglomerates can inflate the P98 and P80 of a part on a cumulative size distribution, and in a normal size distribution, they cause shorter peaks and inconsistent behaviors in the coarse tail, as shown in the image below, which is the highlighted peak is the ultrasonics curve for the same sample, and the unhighlighted peak is the non-ultrasonics curve which is experiencing agglomerates. Agglomerates can be caused by things like surface charge, magnetization, or steric effects, and consistent management of agglomerates is challenging as interparticle attraction can change with grind size. In most cases, ultrasonics helps to reduce agglomerates. However, in some cases, it can make the problem worse. So it's just a matter of making sure that your lab is aware of agglomerates. Red flags to look out for are trends in obscuration readings, either increasing or decreasing, or a lack of repeatability in measurements, which is basically where the sample results and measurements do not overlay, like in the non-ultrasonic example. Sample method has one of the largest effects on consistency and accuracy of the test, and the equipment manufacturer recommends using an overhead stirrer with a baffled beaker to help mix the sample. Subsampling should be done using a pipette from the center of the baffled beaker to ensure that there is adequate consistency. The entire volume of subsampling of the pipette should be emptied into the laser sizer. By only adding partial volumes, a technician can introduce bias as coarse particles can segregate inside the bulb of the pipette. Subsample volume collected needs to also be considered, as adding too much sample can introduce multiple scattering as pictured on the slides, and this essentially produces a finer particle size than what is actually there because you've added too much sample. Best practice is to keep obscuration low, down to as close as possible to 10% to minimize bias. Finally, one of the biggest hurdles for passing the IsaMill accreditation is due to the condition of the laser sizer. Signature plot test work can take a significant amount of time in preparation, running, and cleanup. So to run samples collected on a faulty laser sizer is invalidating all efforts in the test. This example is from a lab undergoing the accreditation test, where they have taken duplicate samples both before and after their laser sizer was serviced. Looking at the results, there's a significant difference in performance just based on laser sizing just based on the laser sizing performance as well. If an IsaMill were to be sized from these results, before calibration, the sizing could have potentially been undersized by up to 30%. So it is always important to ensure that calibrations are up to date, especially when completing stirred milling test work. Furthermore, neglecting equipment can cause some very expensive real-world consequences. To conclude, this presentation aimed to shed light on the challenges of achieving consistency in stirred milling test work. While this is a robust method, it can have its challenges, and it is hoped that when conducting performance comparisons, apples-to-apples comparisons are made, and diligence to minimise bias through the laser sizing method and poor reporting of results is undertaken. Thank you.
Thank you, Kai, and thank you, Jon, and thank you to all for joining today's webinar. That's the end of the presentation. But our team will stay online and they are ready to answer all of your questions on the chat, so please keep asking questions. The slides of this recording and the presentation will be available in the lobby of this webinar, which you can access by clicking on the same link you used to access this session. Thank you again, and I hope really to see you at our next Glencore Technology webinar.